Hi, good evening, everyone. I'm Hasitha Wegiriya from King's College London. My supervisor is Dr. Trishantana Nankara, and our project is supported by PSRC and King's College London Center for Robotic Research. So, in animal world, most nocturnal animals have whiskers, which is cats and mouse. So, inspired from their biology, we have developed a multimodal whisker follicle. So let's see the benefit of the research. So end product of this research will be helpful for firefighters to navigate in the thick smoke. Also will help to recognize the object in low visibility environment. Let's see here is the overview of my presentation. Firstly, I'm going to talk about the morphological features of the biological whisker. Then receptor interface mechanism of the biological whisker. Design of the novel whisker follicle, comparison of two different frequency-dependent data capturing modules. And then finally, the new insights into biological basis of tactile perception using whiskers. So in the morphological features of the biological whisker, let's see the mechanical properties of the whisker and the hypothesis. So, in each whisker follicle responds specifically to the rotation of the follicle by its muscles or to deflection of the whisker shaft by external contacts. So as you can see how the rats move their whiskers from their muscle activity. So, it is also encode information about the direction, velocity, and the duration of displacement and the torque. The follicle has nerve located top and the bottom part of the follicle. So hypothesis is whether the top nerve winding responds to a high frequency vibrations and the bottom nerve winding response to low frequency vibrations. In the morphological features of biological whisker, let's see what happened inside the flesh at the root of the whisker. So the top nerve cell called superficial vibrissal nerve and the bottom nerve called deep vibrissal nerve. And their position is likely to be closely related to type of hair movement that excite them, which is vibration and bending and pulling. Okay, based on the biological inspiration, this is the design of the novel whisker follicle, comparison of two different frequency-dependent data capturing modules. Here, piezoelectric sensors simulate the superficial vibrissal nerve, and the Hall effect sensor simulate the deep vibrissal nerve. And here, the hair follicle represented by the carbon fiber shaft, and which is connected to the piezoelectric sensor through the component connector. The end of the shaft has a magnet, and along with that, in the cylindrical body, Hall sensor is located, and the whole unit is connected to the sensor holder. This is the real novel whisker follicle. As you can see, it's 3D printed cylindrical body with Hall effect sensor and piezoelectric sensor in the front, and the carbon fiber shaft, and the Hall effect sensor inside is embedded in the embedded base, and the piezo sensor and the embedded base connected with the silicon joint. Let's see the receptor interface mechanism of the whisker. In the video shows that the rats do how they do the whisking, and our whisker sensor. Their whisker provide information about the surface properties, objects, and when they're whisking, such as roughness and smoothness. You can see from the second video. It is similar to the human finger. The bottom simulation video shows the generated stress on the base of the whisker shaft when there is a detachment of the whisker tip. This is the simulation when force applied to the whisker tip and the base stress. This is the experiment setup. Here we use the A to D converter, an X5 cable to move the whisker sensor, and this is the plastic pipe that used as the object for the experiment. And this is how this video shows how the experiment is carried out. Let's see the new insight into biological basis of tactile perception using whiskers. This is the Hall sensor reading of 2 speed and 2 indentation levels of brushing the whisker against the object shown. The Hall sensor located over there. The experiments were conducted by 5 speed and 6 indentation level. The plot shows the data from 20 trials for each speed indentation combinations. Inside the orange box, velocity millimeters per second, and blue inside the blue box mentions 20 millimeters per second velocity. And inside the green box is 1 millimeter indentation, and the yellow orange box inside is 5 millimeters indentation. So here y-axis is sensor reading measured from volts, and x-axis is sample rates. So here from the graph shows the increasing indentation caused an increasing magnitude of Hall sensor reading. This is the brushing piezo sensor readings for 2 speed and 2 indentation levels. Again, from the orange box indicates 2 millimeters per second velocity, and the blue indicates 20 millimeters per second velocity. Green indicates 1 millimeters per second, 1 millimeter indentation, and orange indicates 5 millimeter indentation. Here again, sensor reading is volts and sample rates. Here we can see the high indentation cause relative lower peak amplitude in piezo sensor reading from the A and B. But these graphs also show high frequency of vibration for higher speeds, which is C and D. Okay, this is the covariance of the readings of these 2 sensors across the different speed and indentation levels for multiple trials. So in the z-axis for the velocity, millimeters per seconds, and x-axis for piezoelectric, which is from volts, and y-axis Hall sensor reading, which is volts again. The spread of the distribution increases with the increasing speed of brushing. However, the average value do not change significantly. you can see the spread of this distribution increase. So here is the covariance of the readings given by different indentation of brushing on the object shown in the figure. So here again, x-axis for z-axis for indentation, millimeters, and x-axis for piezo sensor, and the y-axis for Hall sensor reading from volts. So in this graph, something interesting observed. The axis of the distribution, the major axis of the distribution rotates to the Hall sensor axis with the high indentation. So piezo sensor data rotates to the Hall sensor axis. So then we look at the average behavior of the maximum eigenvalue of the covariance metrics for Hall sensor and the piezo readings across the different trials, different indentation level and speed of brushing the whisker. Here, high speed of brushing the whisker shows the higher sensitivity to change of indentation. For instance, B and C. The curve corresponding to the speed 4 shows the highest rate of change. The maximum eigenvalue increase and settle down, you can see from this one. And also the average eigenvector angle also settle down in the Seber's region. The angle of the eigenvector with the highest eigenvalue to settle down in the stable region in the figure B. But figure C shows the standard deviation of the variable of the maximum eigenvalue increase and decrease with the increasing indentation. And finally, the figure D shows that the standard deviation of the angle of the eigenvector corresponds to the maximum eigenvalue converges to stable region with increasing indentation level. So let's see the transfer entropy measured by the information gain during the various indentation level across the different speed and levels. Here, information gain on y-axis and indentation increases, indentation on x-axis. The transfer entropy is from G, and the equation is there. So, in this graph shows that the indentation and the speed of a high range of is not going to yield more information. For instance, speed 3 has maximum information gain, but it's speed 4 and speed 5, not up to speed 3, as you can see. And also, after certain indentation, information gain is settled down. It's not going to gain much information. And finally, I can say this is not only provide the new insight into design robotic whisker follicle, but also give an understanding about the functionality of rat whisker follicle. Thank you.
Any questions or comments? Maybe I have one question. So I understand you are presenting about the speed of whiskers.
Yes.
How about the effect of the length of whiskers?
That is called indentation.
Oh, it's different.
You mean the whisker length? Or
Yeah.
yes. Yeah, we have used different type of whisker lengths, but here we consider the indentation, which is the from the object. So how depth we go with the whisker. So, and what is the relative information gain from the two type of sensor models.
Then how about the touching surface? I mean, if you know this very long length,
Yeah.
and you touch at this level, so these whiskers might broken. So
You mean, but this is carbon fiber, so that is why we need to verify what depths we need to go in. So because here we can see clearly if you use more indentation, it doesn't give any information. So only for certain indentation levels and certain velocity.
Thank
you.
Very interesting.
Thank you.
I have a very similar question. Maybe your approach is very good for the continuous, smooth surfaces, but sometimes maybe this is a discontinuous curve. There is a discontinuous curve.
Yes.
In such a case, is it possible to use this?
Thank you for that question. In the future, we are going to do more experiment with uneven object environment. So that is my next step for do that. So yeah.
Okay.
In the future. Yeah. Yeah. Thank you.
So my question is, you are talking about a biological inspired
Yes.
kind of sensor,
Yes.
which is inspired by the mouse.
Yes.
For mouse, it has a series of such sensors
Yes.
that enable it to detect not only whether or not there is a barrier, there is an obstacle, but yeah, it's a series.
Yes.
So, do you have any such kind of algorithms that can gather from a series of sensors to form a full a picture of the environment?
That is a good question. Thank you very much for that. This is for this research carried on only for one whisker, and using two different type of sensor modules. So in a robot application, so what we are going to use multiple whiskers, and then there we're going to develop the algorithm, so how it's going to respond for the environment. So this is basically we're going to focus on firefighters such as disaster zone. So it will be not even environment, so then we're going to use multiple whiskers. Thank you.
So
I hope you get the answers on that.
okay. It's time to finish your presentation. Thank you.
Thank you.